This is the video that you might need to play again and watch and take notes or go through again if you need a recap of all the factoring you did last year in algebra. So having had algebra as the prereq, that's the expectation that you had the factoring. This is just if you need to go back personally and do some more work to get your factoring back into check. So as we go through, factoring means to put something into a form in which you have variables or numbers multiplied together instead of added and subtracted to represent an expression. So numbers, if I asked you to give the factors of 6, you might give me 2 times 3 or 1 times 6. Factors meaning things that multiply. So factors are values that multiply to equal a quantity. Whether that's a number or a variable expression, it doesn't matter. So expressions have factors as well. In chapter 2, we came up with factored expressions for quadratic rules, and then we multiplied or simplified them, or expanded sometimes we would say, in order to turn them into one that was not in factored form. We're working on getting it into factored form to represent things like base and height of a rectangle. So two-factor or factoring is the act of finding the values that will multiply together to equal a quantity. When we're using factoring, we are using integers. We're not using fractions. So all the values you use today would be positive or negative, and they'll be integers. So the first type of factoring that we need to talk about is monomial factoring, meaning we're going to look for something that would reverse distributive property. Distributive property puts a monomial out in front and multiplies it into things. We're going to do the opposite. So by expanding, we'd be going this direction. As we factor, we're going to be looking for what would be able to be written in that multiplied form, or undoing distributive property. You always want to check for monomial factors before you do any other kind of factoring to pull a monomial out. So for instance, the expression that's here, 3y squared plus 12y, you wouldn't go and make this list, but here's what you want to think about. The different factors or values that could be used to write a multiply expression for 3y squared could be any of these in combination to make that 3y squared. A 3 times a y times a y. 12y has different factors. What we hope to find with that GCF, or greatest common factor, is what they have in common and take the largest factor from each. So that greatest means the biggest, common factor meaning one they have in common. I see each list has a factor of y for my variables, so the largest power of my variable, and a 3 for my numerical part. So the largest common factor they have is the expression 3y. And I'm thinking reverse distributive property. If I take the 3 and one of the y factors out, that would leave a y left to be distributed over. If I divide out the 3 and a y factor from the 12y, I'd have a 4. And you can always check that your monomial factoring is correct by distributing back and making sure you get back to your first expression. There are some special patterns you will recall from last year. The one that I think you should be concerned the most about is the one on the right, the difference of squares. The one that's called the perfect square trinomial on this side, we'll go through again, but a lot of times people don't recognize that one right away, but they're still able to factor, and therefore it's not really an issue. So a perfect square trinomial would look in its factored form like an identical binomial multiplied by itself, so it's often rewritten after you factored, it's often rewritten that way. Where it came from, however, was an expression that we want to look for a pattern in. X squared plus 14x plus 49 would be the expanded form of that. And if you notice, it starts with a perfect square and ends with a perfect square. And the value in the middle is the number 2 times each of the values that the perfect squares came from. So an x and a 7 times 2. So that this 14x is 2 sets of 7x put together. If I expand this expression, I'd have x squared minus 6x plus 9, if I use distributive property. Some people call it FOIL when it's 2 binomials. And if you notice, it begins with a perfect square of x, it ends with the square of 3, and in the middle, or negative 3, in the middle it's 2 sets of a 3 times an x put together. So this one expanded would look like x squared plus 8x plus 16. If you recognize that pattern in the trinomial, people can often then write the factors very quickly. This is the pattern where if you don't catch it in the trinomial, you'd still be able to factor it easily by some of the other ways you may think about factoring. So in math speak, it would look like a squared plus 2 sets of the a and the b multiplied together plus b squared, or if there's a subtract, it would look like a squared minus 2 sets of the first and the second plus that squared. Again, not going to ask you for the specific name of that pattern, but you might want to recognize it. The one that more people recognize is when the two factors multiply together to produce a pattern in which you have a perfect square minus a perfect square. And it's called difference of squares. This one's an important one to recognize because it makes your factoring go more quickly. So if I recognize that something is this difference, perfect square, subtract perfect square, I can turn it back into my factors more quickly. So in math speak, if I recognize that I have something in the form perfect square minus perfect square, its factoring will take us back to expressions that use the square root of each of those perfect squares, one with an add, one with a subtract. Binomial factoring, trying to put our factors after we've gotten the greatest common factor out, then trying to put it to binomial factors, two-term expressions. And one way is grouping. In the second video, we'll go through it with trinomials. But one way is grouping. So in a group, we still want to look to see, I have 4 total terms. You want to group terms with common factors and look to see if anybody has a common monomial. Throughout all 4 terms, I don't see a common monomial for all 4. But if I just take it in groups of 2, and sometimes you need to rearrange your groups of 2, I see that there's a common factor of 2 and of y in the first set. And if I distribute in reverse, I'd have x minus 1 as the factor they multiply by. And in the second set, I see that a plus 7, so that I still have addition here, is the common factor, and I could take out the 7 from both terms. This is not factored yet. I have it in 2 groups now instead of 4 separate expressions. In the 2 groups, I notice that both have something distributing over x minus 1. So what I would list out front to put it to its factored form is what needs to be distributed over that x minus 1 expression. And I see that a 2y needs to be distributed over that, and a 7. And that becomes my other factor, and now that's in factored form. If you want to check it, you can certainly use distributive property and make sure that that comes back out. So putting this all together before we end this video and start the second one, when I see an expression, I still want to check for my GCF factor. If the GCF for all 4 terms is 1, then I want to keep going and try grouping or some of my other factoring, but I definitely want to take out the largest common factor from all the terms first. And I happen to notice they're all even, so there is at least a factor of 2 that could be factored from each expression before we start that factoring by grouping or anything else. That 2 now will just be a factor that continues down with the rest of this as I go to work on the rest of it. The rest of it now I'm going to factor by grouping. I'm going to take these 2 terms and find out what they have in common. Their greatest monomial factor is a y. And in the second group, I would really like this 4x minus 3 to show up again. So what I'm noticing here is that they're both multiples of 5, but even better, to get that plus 3 in there, they're all multiples of negative 5. So my monomial factor that I'm going to divide out of each of those in my second group is a negative 5, so I'll be left with 4x. And then when I factor the negative 5 out of negative 15, I get a plus 3. So now I have 2 groups that have the same expression in them. So I will have 2 sets of, and my binomial factors come out now. The 4x plus 3 is a factor that has 2 distributors. Y needs to multiply by it, as you would with FOIL, and a minus 5, and I'm factored. So factoring by grouping is great when you have 4 terms.